my name is Weitao, and today I will be presenting my work with my professor, T.S. Eugene. And our topic is to use one network telemetry to give a weighted bandwidth allocation at scale. And I really appreciate the last talk about sequential program optimization. I tried to fit my work into that, but it may or may not be a sequential program. So let's get started. So data center network will interconnect all the servers we have in the data center. And it's usually a multi-layer network. And on top of that, we run tons of applications. But with the complexity of the application increase, we have a larger and larger data center, and so that we have a larger and larger network. So the focus of this talk will be focusing on the bandwidth resource sharing for the data center network. So for data center, all the major cloud providers try to use decentralized congestion control to do bandwidth sharing because it's low cost and have very low overhead for such large scale cloud. But there's no explicit considerations for proportional resource allocation or weighted resource allocation. So our target is very simple. We try to achieve weighted allocation with very low overhead. Like for example, in this case, we have a higher weight or higher priority for the orange flow. So the orange flow gets higher bandwidth than others. And the content in this talk will be firstly talking about how can we do weighted allocation on a single link with just one signal. And then we'll talk about the weighted allocation in an arbitrary network. So challenge about changing the weight or changing the rate allocation is we want to do it with minimum information exchange. For example, the orange flow here want to increase its rate allocation, but it don't want to inform others or inform any centralized controller. If we try to give all-to-all communication between all the flows or all the resource participants, it will incur very high overhead. If we want to introduce a master controller, it will add additional communication latency and overhead for doing that. So both of them are not feasible in a large-scale data center network. So then we turn our focus to the network links because flows all shares the same bottleneck links. And the one question we raise is that, can we use the bottleneck link to exchange the information for all the flow participants? So let's firstly consider a very, very simple case where there's only one link and there are multiple flows with different weights on it. So we denote as flow 1 to flow n and weight 1 to weight n. So their rate allocation is supposed to be R1 to Rn. And for any flow Rk, this is a very simple math. We just let weight k divided by the sum of all the weights times the bandwidth. So this is the rate allocation should be. So this is our goal. We want to achieve this weighted allocation. So firstly, what we want to do is we want to split this equation into two equivalent equation sets. So one is R1 plus Rn is equal to B. And the other one is R1 divided by weight 1 is equal to any Ri divided by weight I. So you can prove those two equations are just equivalent to the goals we want to achieve below. And you can see those two equations just reflect the two targets we want to achieve here. So the first equation represents full utilization for the link. The second equation achieves weighted fail for all the flows. So next question is, can we find a signal that indicates each of the equations are achieved or reached, or guide us how to reach each equation? So we turn to this very simple annotation about a queue in front of a link. So if the link receives input traffic that is larger than its bandwidth, the queue in front of the link will increase. If the input is smaller than bandwidth, then the queue will decrease. And if the input is equal than the bandwidth, the queue will be stabilized around a certain level. So with these insights, we can see that if we can find the queue will stabilize around a certain level or any level, we know all the input rates, the sum of all the input rates is equal to the bandwidth. And this queue level need to be larger than 0 to indicate the link is fully utilized. So by observing whether the queue is stabilized, we can know whether the first equation is achieved or not. So then what about the second equation? How can we know every flow's rate divided by weight is the same? By just observing the queue length or the queuing delay. So you can see that the queue can be stabilized at any level to indicate the first equation is achieved. So can we use the queuing level to indicate the bandwidth allocation status? So we try to create a mapping between the queuing and every flow's rate divided by its weight, which is a proportion rate. And specifically, we designed a mapping between the rate by weight and the queuing delay we observed. So this is the equation we have for the specific mapping, and I also draw it here on the graph. So as you can see, when the rate divided by weight increase, the target queuing delay will decrease. And you can see a smaller rate by weight will have a higher target queuing, and the higher rate by weight will have a lower target queuing. But if all the flows share the same bottleneck link, they will observe the same queuing length. And this observed same queuing length will indicate an anchor rate divided by weight. And if we try to pull every flow towards this anchor point, it will finally converge to a final state. So this is how we converge the every flow's rate by weight to the anchor. We update the new rate based on the anchor point and its current status. So in these two figures, we show that in the final state, every flow's rate divided by weight will converge to the same final state, which is 1 point. As you can see, the orange flow has higher rate by weight. It will decrease its rate. The blue flow will have lower rate by weight, so it will increase rate. So in the end, every flow's rate divided by weight, its target is equal to the queuing. So all the flows on the same link will converge to the same final states, and then the system will stabilize. So this final state can be described as a target of bandwidth divided by the sum of all the weights. So the observation we find is that with this convergence algorithm, the sum of the weights determines the converged queuing length. So when the sum of all flow weights increase, so each shell of the bandwidth becomes smaller, and then the converged queue level will increase. As you can see, the per shell rate will decrease, but the target queuing level will increase. This is the convergence point will change, will move. Similarly, when the sum of all the flow weights decrease, each shell of the bandwidth will become larger, so the converged queuing level will decrease. So by control the final converged queue length, we could indicate every flow how to update their rate so that they can converge to the final point. So in this case, with this capability, we propose our system Söze. So it can let one flow pretend to be multiple flows. So when every flow's weight is equal to 1, it will have a normal file allocation. When the weight is smaller than 1, this flow will be altruistic. It will give its own bandwidth to others. When the flow is larger than 1, it will have some prioritization allocation, which means it will grab more bandwidth. Yeah, so in summary, a flow can disguise itself in our system by changing its input for the target function we described before to be smaller or larger so that it can get higher or smaller bandwidths. So for a single link, the convergency can be proved in our paper. So you can find the detailed proof in our paper. But we haven't talked about how can we identify the bottleneck hop from a multi-hop scenario. So how do you find the bottleneck resource in a graph of links rather than just a simple one link? Remember, our target function is special designed to be monotonically decreasing. So on one side, it was for convergency purpose. On the other side, it also helped us distinguish the bottleneck hop from all the hops that one flow traverses. This is because the largest queuing always means the most severe contention in our case. So in this simple example, the first link's queuing is stabilized around the target of 25. And for the second link, the queuing was stabilized at a target of 50. And from this graph, we can easily see target of 25 is larger than the target of 50. So which means the queuing on the contention on the first link is more severe, so that it becomes the bottleneck for the orange flow. So that orange flow will always react to the congestion on the first link and ignore other links. So that's why we can only collect the largest queuing delay on the forwarding path. And in an arbitrary network, the convergency can also be proved. You can find the proof in the paper. So to recap the Söze's design, we use it with the CSIC format. So CSIC is Google's now telemetry standard, which is released in 2024. It will collect the bottleneck hop signal on the forwarding path. In this case, it's a maximum queuing delay. As you can see, when the packet moves, it will update itself with the highest queuing on the forwarding path, and then use the acknowledgement packets to send this information back to the sender. So after using this CSIC format in our system, every flow will obtain the maximum queuing delay from the network, which will indicate this is a signal from the bottleneck hop. And given the maximum delay and its own flow weights, every flow will adjust its rates with the design update function. So this is how we collect the information from the network and then update, let every flow independently update its rate to reach the global optimal status. And note that every flow needs to follow the same policy, which is described in our talk. Otherwise, the whole system cannot converge. But this is definitely doable in a controlled environment, especially in a data center network. So for implementation, we implemented it in both a Linux kernel modular and also a kernel bypass implementation, which is the ERPC. And for evaluation, we first compile Söze with other CC algorithms. Here we picked HPCC and DCQCN. So you can see under both 40% load and 80% load, CC already outperformed all other CC algorithms without weight adjustment. So this is standalone as a CC how it performs. And for the weight update micro benchmark, we try to increase the weight for the blue flow here. This blue is a one flow here, from 1 to 5. As you can see, when we increase the weight for the flow 1, previously the bottleneck is switch 1. And after the weight increase to be higher than 2, the bottleneck switch to be switch 2. So which means the bottleneck switch from switch 2 to switch 1. And then the flow 1 will have higher bandwidth allocated. So you can see it's roughly the same trend as a weighted round robin in the switch with the AMD algorithm, but it achieves more accurate rate enforcement. And here we also comparing with a centralized solution, which is a water filling solution. As you can see, even with different factory topology size, which means in larger and larger network scales, the convergency for our system to the weighted allocation is always a constant time. And we can also enforce our weighted allocation very accurately with any arbitrary weight specified. So in conclusion, we try to use maximum queuing delay signal to coordinate the flow centers rate adjustment. And we can identify the bottleneck resources and converge into weighted maximum allocation. And lastly, we enable every flow to update its allocation without direct coordination with other flows. You just try to change the equilibrium and change the final convergent state to change the rate allocation. So I'm happy to take any questions.